Now, in the next few lectures, we're going to focus on Le Chatelier's principle. And this is really just a way of looking at equilibrium when it's disturbed from equilibrium and how the system goes back to it, or how we reestablish equilibrium. So we've already worked on this conceptually. When we worked on that demonstration of what equilibrium is, and we were just moving toys back and forth for reactants and products, after we reached equilibrium, we removed some of the products, and then it took about one turn or two turns before equilibrium reestablished itself. And we saw a different rate of toy transfer, but it was still the same as in the forward and the reverse. And we had the same ratio of products to reactants. And then we took away some of the reactants and we saw the same thing. It took a few turns to get the same rates established. But then we saw that the ratio of the products to reactants was again the same. And so we're going to look into that in a bit more detail here. We're going to look at concentration. We're going to look at volume. We're going to look at catalysts and temperature and the different ways we can affect equilibrium. All right, so once a system is at equilibrium, if we change anything about it, we won't be at equilibrium anymore. We call this a disturbance to equilibrium or a stress on the system. You might see a couple of different ways that it's phrased. And so what the system does is it reestablishes equilibrium because that is where our rates are equal, and once dynamic equilibrium is established, it kind of maintains at that state. And so to get back to that state, we'll see the system change the rates of either forward or reverse reaction to get back to that same ratio of products to reactants. And this is all described in what we call Le Chatelier's principle, which states that if a system is at equilibrium and is disturbed, the position of that equilibrium will shift to minimize the disturbance. So let's break down this language here and describe it a couple of ways. So shift means to see the one of the rates, either forward or reverse, increase relative to the other or decrease relative to the other. So we see our rates will have to work to get back to being the same. And the goal here is that by minimizing the disturbance, we're really trying to reestablish equilibrium. And that's just going to be defined as that ratio between our products to reactants. So I actually have that written over here. So once we are when we're initially at equilibrium, our Q is equal to our K, right? So we're at equilibrium. And then once that disturbance occurs, we're no longer at equilibrium, which means that our Q is different than our K now. And so if our Q, we just talked about Q, right? If our Q is larger than our K, then we're going to form more of our reactants to reestablish that equilibrium and to get back to K. And if our Q is less than K, it's going to form more products to form a ratio of products to reactants that will equal K. And so really this is just an exercise in saying like, well, what needs to change to be at equilibrium again? If I have too many products and less reactants and my Q is larger than my K, so that would be this right here. If my Q is larger than my K, then I actually need to make sure the reverse reaction is happening more than the forward reaction. And I'll convert some of those products into reactants. And then I'll do that until I hit that balance of product to reactants that is defined by the equilibrium constant. And so we call this shifting to the left. And that's when the reverse rate is going to be greater than the forward rate. And that'll happen until the rates are the same. And when those rates become the same, we'll see that our Q equals K again. And we call this shifting to the left because it's the reverse reaction that's happening more. And so if I have my double arrows the same equal size between my reactants and products to represent equilibrium, I would say that what's happening here is that my reverse reaction is larger than my forward reaction, or the rate. And so I tend to write these arrows like this, where I'm showing which one is bigger to represent which of those rates is dominant. And so this is going to be, and the language we're going to use here is calling it shifting to the left. Some other ways you can say it is the reaction will form more reactants to reestablish equilibrium, or the reaction will shift left to reestablish equilibrium. I'm okay with either of those. Your textbook will probably use shift left. And that's kind of the primary way that we think about this and discuss it in chemistry. But this language is kind of specific and it takes some practice. It's not, this is like learning a new language right now. So let's think about the other one, where something happens to the reaction, and now when you calculate that mass action quotient, or that mass action expression, which remember is this right here, then what we have is a Q that is less than K if we calculate it. And that really means that we have more reactants than we had products when our ratio of products to reactants was at equilibrium. And so it's kind of like we need to make more products. We need to take some of these reactants that we have and we need to convert them into products more than we're converting products into reactants. So that way we have this kind of net shift to increase the products to get back that balance that is equilibrium. And so we call this shifting to the right, and it's when the forward reaction is dominant. So our forward, let's abbreviate that differently. So our forward rate is larger than our reverse rate. And the way I would represent these arrows is a larger arrow to the product side and a smaller one to the reactant side, to show that it is the forward reaction that is dominating the system at the moment to reestablish equilibrium. And I will like highlight this again. There, especially when learning about equilibrium for the first time in terms of reactions, there is a language barrier here. We're going to talk about this with a language constructed just to talk about equilibrium. And so this is kind of the language lesson of chemistry. And so there is the concept to understand, but then it's sometimes a little obfuscated when we bring in the language that we use to talk about it, especially since there's kind of a few ways to frame it. I'll try to give you a couple different examples of it, but also pay attention to this in the lectures in the book, and be aware that it might take a little practice. And if it feels confusing, you can double check the language with me. One of the key things about this that I think can be confusing is that we're looking at a system that is in balance, right? So I'm going to become a scale right here. So we're going to pretend that I'm at a reaction at equilibrium. Here's my reactants and here's my products. And oh, I can even use signs. Okay, so I'm balanced. This is kind of hard to hold. My reactants and my products, and so I'm at equilibrium. And it doesn't mean I have the same amount, but we have the same rates. We'll say that. So if something happens that disturbs equilibrium, and I have a lot more reactants than I have products around, I'm no longer at balance. And my goal is to get myself back to that balance of equilibrium. So the first thing that happens is I'm at equilibrium, and then there's a disturbance. And a lot of times that change is described. It's like the product concentration is decreased. What is the effect? Like, how will equilibrium shift to reestablish itself? That might be how it's phrased. And so a lot of times everyone says, oh, well, there's less products now. That's how it's changed. But we don't really care about this initial change. We care about the next change, the change of how do we get back to balance. So all of our questions about equilibrium will be about not the first change that creates the disturbance, but rather what is the change that reestablishes the balance of equilibrium. And so in this case, if I have more reactants and products, I would say, oh, well, the rate of converting my reactants to products, the forward rate, needs to be bigger than the rate of my products forming reactants. So that way I have a net increase in the amount of products relative to the reactants. And I see the increase in the product concentration as the reactant concentration decreases on a macroscopic level until they hit equilibrium again. And so we're talking about that second change and how it shifts. And so we could say the reaction would shift when we're doing this one with our reactants and our products. We could say the products increase to reestablish equilibrium. Or we can say the reaction shifts to the right to reestablish equilibrium. All right, let's look at what happens as we change concentration and how we see a change in the system to reestablish equilibrium. So I've got an example here. It's 2 sulfur dioxide plus 2 oxygen forming 2 sulfur trioxide. Now, these are all gases. I've written out our Q expression up here in the top left-hand corner. And I'd like to start by first distinguishing the two types of change we're seeing here. So the first type of change described is right here. And I'll just start with the first one by example, where I'm increasing the concentration of SO2. So I'm assuming that I am at equilibrium. And then I increase the amount of SO2. That's my first change. Now I'm no longer at equilibrium. The change I'm interested in is how is equilibrium reestablished? How is the system going to minimize the disturbance by shifting equilibrium to either the right or the left to form more products or reactants? So what we're interested in terms of like answering questions on problem sets or case studies or on homework is this piece here at the bottom that we're going to show right here, which is how does the system reestablish equilibrium? How is that disturbance minimized? That's the change we're going to report. We're not going to ever repeat, oh, well, if we increase SO2, we're increasing the reactants. Well, yeah, we are. So that's what happens next is the question. So let's talk about that. So we increase sulfur dioxide. That's going to increase something that's on the denominator of our mass action expression or equilibrium expression. So when we do that, we're going to see that we'll calculate a value that is smaller, right? So if this increases in my fraction, if my denominator increases, then the number I'm calculating will decrease. And so I'm going to see that my Q is going to become less than K. I used to be at equilibrium. Then I increased the amount of my SO2 and I was no longer at equilibrium. I have a K, a Q, a reaction quotient that is now smaller than K. So how is equilibrium going to be reestablished? We just talked about this. It means that we're going to need to have a faster rate going forward. So that way we're creating a net increase in our products to rebuild that balance that is defined as equilibrium, where I have the same ratio of products to reactants. And so I'm going to say this is going to shift to the product side. It's going to shift right. So I can say either shift to products or shift right, or I can say shift to form more products. In fact, let's just kind of write all of these options out that you could, the way you could phrase it. So you can say, let's write it out. Okay, so we can say that the reaction shifts right, it shifts to the product side, or it shifts right to form more products. All of these are fine with me. And it'll do this until Q equals K. All right. So given that, what happens if we increase the other reactant? What if we increase our oxygen here? Well, if we increase our oxygen, we're going to have the same effect that we saw with our SO2. We're going to see a decrease in our Q value. This will be the same. So again, our Q is going to be less than our K, and we're going to shift to the right. And so we can actually extrapolate here. We can say that anytime we increase the concentration of a reactant, the equilibrium will be reestablished by shifting the reaction to the right. Okay, so let's look at the opposite now. What happens if we decrease our reactants? So I can look at SO2 and I can look at O2. So if either of these are going to decrease, or if both of them are going to decrease, then I'm going to have a smaller number on that denominator, which means my overall value I would calculate would be larger. So I'll see Q increase when I do that. So when Q is larger than K, so this will happen for both of these, then really we need to see a net movement of products to form reactants to reestablish that ratio of product to reactants that defined equilibrium. And so we're going to see the reaction shift to the left to do that. And it really just means that the reverse reaction is going to dominate when we say that. And we can generalize this and say that any decrease in our reactant concentration will lead to a shift to the left to form more reactants. All right, let's look at products. What happens when we change those? So if I'm going to increase my product, I'm really focusing now on a change to that concentration in the numerator. And so if that number gets bigger, then the Q value gets bigger as well. So this will be a proportional change. So as this increases, so does my Q value. And so that means that if I have Q larger than K, this is going to need to shift to the left. So that way we have a net transfer of products to reactants that overall we're going to favor the reverse reaction. It's going to go faster until they're equal. And we'll, from like a macroscopic perspective, see an overall increase in the number of reactants that we have. So I could say that when I increase products, I'm always going to see a shift to the left to reform more reactants. Now, what happens when we decrease our products? Well, if I see a decrease in that concentration, I'll calculate a Q value that is also smaller, right? When that numerator value is smaller. And so when that happens, then I'm going to have a Q that's less than the K that we had. And just like what we saw before, oh, wrong sign. If that Q is less, it's going to need to convert some of those reactants into products. So it's going to favor that forward reaction. So I have a net increase in the amount of products I have. So that way I can recreate that ratio of concentration of products to reactants that was defined as equilibrium. So I'm going to see a shift to the right. And you can abstract this as well. You can say that whenever you decrease the concentration of products, you're going to see a right shift. And so this is how we'll see systems behave when we're looking at changes in concentration. Next, we'll look at what happens when we change volume, if everything is a gas, and what happens if we change temperature.